today. So for the purpose of this talk, X compact Kähler manifold will be called hyperkähler. I'll abbreviate HK for short if it is simply connected and if there exists a holomorphic symplectic form. So that's 2-0 form closed, and that's non-degenerate. Non-degenerate. So holomorphic symplectic form. So you see that if X is a hyperkähler manifold, in particular, the complex dimension of X is always even, and the canonical bundle of X is trivialized by the max tensor exterior product of this form. So one reason why we care about these hyperkähler manifolds is that they are the building blocks of varieties with trivial first-term class. So together with abelian varieties, and with Calabi-Yau. So essentially any variety with trivial canonical bundle can be written up to a finite cover, étale cover, as a product of abelian varieties and of Calabi-Yau manifolds. So an example, the first example of a hyperkähler manifold is S, a K3 surface. So what is a K3 surface? You can think of the zero locus of a polynomial, a homogeneous polynomial of degree 4 in P3, and all their deformations of such a thing. And it's not hard to check that it's simply connected, and that by adjunction formula that there's this holomorphic symplectic form. So in some sense, these things are higher dimensional analogs of K3 surfaces. And indeed, most of the examples that we know of such things come from K3 surfaces. So we saw in Leah's talk that if you take a K3 surface and you take the symmetric product, so this just parameterizes points on S such that total, with some multiplicities, such that total multiplicities is equal to n. This admits a natural resolution called the Hilbert scheme. Where you don't only keep track of the multiplicities, but you kind of look at in which directions you have the multiplicities, sort of. And so the important fact here is that, so on the symmetric product, on the smooth locus, so the symmetric product is singular, but away from the diagonal it's smooth. And this symplectic form on the K3 surface induces one on this product. So we have this symplectic form here. And the important feature of this map is that the pullback of this thing extends to a holomorphic symplectic form everywhere on all. So this is a resolution of the singularities. So where it's smooth, it's just an isomorphism. So you bring it here, and then you extend it from this open subset to the whole thing. So such a map is called a symplectic resolution. So in general, if I have a quotient, for example, I have C2n with a standard symplectic form, and I take the quotient, this guy admits a symplectic resolution only when n is 1. So this is just to say that the fact that this map even exists is a very particular thing of this example. So there's a similar construction that I won't be talking about, but where instead of having a K3 surface, we have an abelian surface. The other examples are when you take moduli spaces of semi-stable vector bundles. So if M is one of these moduli spaces, Mukai showed that there is an open subset of stable vector bundles, and this guy here is smooth. So the moduli space is projective, but in general it's highly singular. But then there's this nice open subset that is smooth and has a symplectic form, a holomorphic symplectic form. So if this nice open subset is the whole thing, then it was showed by many people that this moduli space is deformation of one of those examples. So, but in general, this isn't the case. So in general, M is singular. So a question is when does M admit a symplectic resolution? So it was answered by O'Grady. And he found two examples where M does admit a symplectic resolution, but in all other cases it was proved that it does not. And so these two examples provided new examples that were not deformation to the known examples. But in general, these are the only known examples. And in fact, a question that has motivated a lot of work in the area is are there other new examples? Are there new examples? So it could be that we know all the known cases, all the known examples, but so some of the work that I've been doing was to try and find new examples. But in general, so this definition that is quite simple is pretty restrictive. And one instance of this fact is the fact that we know very few examples, and the other fact is that there are very few maps from hyperkähler manifolds. And so an instance is the theorem Matsushita, which says that if X, so if X is a hyperkähler and B is a normal and pi is proper and surjective with positive dimensional fibers, then something pretty amazing happens that pi, so the dimension of B, so if x was 2n dimensional, dimension of B is equal to n. So it's half dimension. And pi is a Lagrangian fibration. So by this I mean, so the general fiber is going to be an abelian variety, but all the fibers are Lagrangian. So this just means that each irreducible component, the pullback of the symplectic form to each irreducible component of the fibers vanishes. And so in particular, the map is equidimensional. Which is a pretty strong fact. So essentially, all the maps from a hyperkähler can be either a Lagrangian fibration or a symplectic resolution. So either a Lagrangian fibration or a symplectic resolution. So I mean a birational map such that this thing here is singular but has a symplectic form on the open locus. Yeah, sure. Yeah, positive dimensional. Positive dimensional, so, and B. So, yeah, the dimension is between 0 and 2n. But so, as an example, if C is a K3 surface, C is a curve of genus G on a K3 surface, it's known that as G moves on the K3, as we consider deformation of C, they parameterize a projective space of dimension G, and one can construct a hyperkähler manifold that I'll denote in this way, such that if I have a point here corresponding to a curve, say a smooth curve CT, then the fiber will just be the Jacobian variety of this curve. And and this is Lagrangian fibration, in fact. And essentially all known examples of Lagrangian fibrations in principally of Lagrangian fibrations in principally polarized abelian varieties, at least in this class of hyperkählers that are deformation of Hilbert schemes, are Jacobians. And so it's interesting to provide examples where you have fibrations in principally polarized abelian varieties that are not Jacobian of curves. So there are examples, for example, in prim varieties. And Markushevich and Tikhomirov, and some work with Arborello and Ferretti and myself, or in intermediate Jacobians. But all these examples are not either they're only quasi-projective manifolds, or if you can compactify them, the singularities don't emit a symplectic resolution. So I think my time is up, but so I just wanted to say that kind of questions that I'm thinking about now is how to exploit these two maps to find these two kind of maps to find information about the geometry of hyperkähler manifolds or about their moduli spaces, since there's a lot of structure that can be said about both this map and this map. I should say it's a semi-small map. So there's a lot of structure about these things, and I wanted to do some examples of how you can sort of get information about moduli spaces starting from these things. But since my time is up, I'll just stop here.